welcome to Surge. I'm giving a talk I haven't given before. I have no timings on it, so I'll either finish really early or there will be slides online. I wrote a book called Scalable Internet Architectures, and when I wrote it, I really didn't want to write a cookbook because I don't want you to make the same recipes I do. I wanted to write a book about the way people think. And a lot of people have asked me over time, like, no. I want a pattern to follow. I want to be able to, can you take the gain down just a little bit, Miguel? A little bit? Okay. All right. Is that too loud? Everybody? Yeah? Echo. That's awesome. All right. That's good. Perfect. All right. So, they said I want patterns. I want a template. I want a cookie cutter so that I can go do it. And I think that that's impossible. So what I'm going to talk about is some different concepts that do and don't work, which is truly ironic. I'll get into that. So I'm the CEO of OmniTI. We build big stuff. I'm an engineer. Brian Ketchel mentioned the ACM, of which I've been a member for 11 years. I'm also a member of IEEE. And like John also said, I think it's absolutely essential that we become more connected with the academic community. And Brian is also right in that they do not serve us very well. And sadly, they don't listen very well. I was in academia for a long time. I remember when my ears didn't work. But we can change that. And there are a lot of smart people that are motivated in solving hard problems, and more brains on hard problems is always better than less brains on hard problems. So by participating in these professional organizations that tie into academia, you have a voice. You have a power to influence the output of those organizations, and people will listen. So we can get really interesting research done on topics that are actually germane to what hurts us on a daily basis, right? Almost every product I've ever worked on has been born from pain. Of course, it's been a good product because it made me personally. And I think that participating in these professional organizations is really essential to that. I do a lot of open source code. If I can't read the code, I don't trust it, usually. Not that I won't run it, but it's very hard to trust things that I don't understand. And by reading the code, I understand at least how it's intended to operate. And I have a bit of experience. So I work in a consulting company. We've been in business 13 years, and we've had clients across every different vertical, right? Financial services, health and human services, lotteries, social networking, all sorts of stuff. And what's interesting is that all of their problems are different. But then as you regress into the academic problem space, they're actually a lot alike. But nobody talks to each other. All the social networks, not all of them, but most of them, they run out of a very small collection of technologies. And it's because they steal completely from each other, right? You get the engineer, LinkedIn grabs somebody from, another social network like Friendster, Facebook, and all these other things are just with each other. You have this insular thought pattern. And it takes a rather large organization to pull in fresh talent to think differently. And we see that a lot. We go into financial services, and we're seeing these social networks look at these problems and like, oh my God, they're web scale. Right? These are huge, and financial services does 10 times as much traffic. Like, I'll never be able to do 5,000 transactions a second on my database. And I'm looking at the financial services group, and they're like, well, we did 50,000, but we're not near capacity. It's like there's some impedance mismatch here, right? People aren't listening to each other because they're not talking to each other. So, before I jump into monitoring, I thought I'd talk about what works and what doesn't. So the irony of this, one of my favorite mantras is the right tool for the job. And as some of my colleagues would know, there's a bit of hypocrisy in that on the surface. I remember I went into our New York office, and the whiteboard was sitting on the floor there. It hadn't been hung up yet, right? It's like, it's been up here for like 4 months. Like, what's going on? Why is it not hung up? It's like, well, we have screws, screwdriver handy. It's like, we have a hammer, we have screws. Like, 4 months later, I'll make this work, right? Bam, there's a whiteboard hung up. It's level, wasn't pretty. Behind it, but it worked. The reason that that was the right tool for the job is because the job wasn't getting done. And the irony of what works is how many people here have knocked a nail into something other than a hammer? Right? Okay? A sufficiently capable technologist can make anything work. It all works. If my database has corruption and loses data, I've seen this before. I don't want to switch technologies, I'll run 4 of them. Right? If 2 of them agree, then that's the data. It's awful, but it works, right? So the interesting part in all of this is you don't want to have to compensate for all of these failures, right? You don't want to compensate for all these problems in technology, but they exist anyway. So at some level, you will always be doing this. It doesn't excuse choosing the wrong technology. There's also no excuse in failing either. So it's an interesting balance that we all have to arrive at, right? If it doesn't work, it's because you're incompetent. And if it does work, you still probably did it the wrong way, right? This is like the reality that we have to deal with. So here are some hints. Like the talk is about hints of trying to approach things from the right perspective. The first thing I'll talk about is monitoring, because I've had my head in that for the last 12 months. Monitoring is what you're looking at. And the correct answer is everything. But the status quo for monitoring, how many people here monitor their stuff? There we go, all right. So how many people monitor the metrics that your things expose, right? You run MySQL, you do a show status, it's got like 40 variables, you monitor that, right? You monitor those things, you monitor SNMP, you monitor disk IO. Those are all prefab shipped items that have nothing to do with your business at all. Not saying that they're not important, but there's a typo on the side that should not be worthless. It should be worth less. All of those metrics are worth less when they are not correlated or coupled with actual metrics that are germane to your business. How many registrations do you have? How much money do you make? All of those things are absolutely critical because it's not just about technology. So, your business is not likely an infrastructure as a service. I'm sure there are people here that sell platforms as a service and infrastructure as a service. If you're not one of those, how many people here actually build their systems on top of the cloud or in their own data center? Or build systems that you don't sell to other people as infrastructure? How many people here run EC2? Not use EC2, operate EC2. Operate, well, you don't do it anymore, you can't. Operate joint, operate Rackspace Cloud. Those are the people whose business it is to sell you virtual machines, CPU cycles, IOPS. Your customers most likely are not buying IOPS, storage, IP connectivity, and CPU cycles. Right? They're buying some sort of meta service built on top of that. So the metrics that are coupled with that are absolutely critical to tie into your monitoring system, because otherwise you have developers, engineers, operations, all of these people, even if you wrap them together, that are looking at stuff that has no meaning. Oh, my system is, latency is too high. Really? What's too high? Does it damage monetization? Are less users coming? Are less users converging? Right? I've seen people look at a system that has like 400 milliseconds of latency, and they're just like, I got to get to 350. And you ask them why, and they have an okay answer to that, which is, I read a Microsoft study that said every 100 milliseconds of latency causes 0.2% of permanent user attrition. I'm like, okay. That's interesting. That's for Microsoft. I believe that it was for us if you show me that. Show me user attrition. Show me who's looking at the website. And don't optimize this from 400 to 350. De-optimize it. Take it from 400. It's easy to add latency. Add 50 milliseconds latency. Add 100 milliseconds latency to 10% of the user population. Show me that it matters. Because then we'll fund speeding it up to 350 milliseconds. Right? These things are in a vacuum a lot of times. The business, marketing, all of that's in a vacuum. So it needs to be tied together. Monitor everything. All right. So then once you have everything monitored, there are different things you need to do with it. You need to correlate them. This, a lot of times, only happens in the mind's eye, which is actually very good. Right? right? You have operations people, you have developers that are looking at their page load times, you have operations guys that are looking at their IOPS and their latency, and you have business guys that are looking at their campaigns. Did my email go out on time? Did my website conversion traffic from this ad campaign by Google AdWords work correctly? What was the convergence rate on those users? All of that information. The problem is we have these 3 different sections, sometimes 4 or 5, that are all looking at different things. You've got ops guys looking at something like Nagios or Zabbix and maybe some cacti stuff. You've got developers looking at the output of O profile or APD or stack trace web performance centric stuff. You've got business people looking at Excel and crystal reports. And it's funny, I mean, you laugh. There's a lot of business people that look at an Excel report and say there was a problem with website yesterday at 11:30. And you're like, no, that wasn't. And then they say, you go for an hour and find out what it was. And you come back and you're like, somebody pushed change that we didn't know about, and yeah, there was some sort of interesting users that were already logged in couldn't change accounts. How'd you know that? Like, Excel doesn't lie. Everybody needs to look at the same thing. It's important to correlate these things. The other thing, which is one thing that I've learned from Mr. Oswald, is that we need to plan, right? And a lot of that has to do with projections. The cloud is a crutch. Right? It's a useful crutch, but the idea that I can spin up 1,000 new instances tomorrow means that I have a chainsaw, I can go cut down 500 trees, right? I can do that too. Why should I do that? What do I need? Why wasn't 1 tree enough? Right? I shouldn't ever need to just spin up 1,000 instances tomorrow or next week. I should have a plan. It should be more than a week out. Right? You read the press release from Zynga, you're like, we're so successful, we actually now have to provision 1,000 new servers a week. I think of that innovation is the problem. 1,000 servers a week. And this has been going on for some time. It's far approaching Facebook size, right? And there is a problem. You're telling me that many billions of CPU instructions is not enough, or memory bandwidth, or network bandwidth. And you come back to the things like the Ruby on Rails conundrum, where I have a cluster of 4 boxes and I get 3 requests per second across all of them. Not because Ruby sucks, it's because the developers sucked, right? But somehow from the business perspective, that's acceptable. So you just say, 3 requests per second, I need to go to 30,000. I just need to buy 40,000 machines. And you kind of lose perspective on that, because people see numbers like 3 requests per second and they laugh, and then you look at a 300 requests per second and they don't laugh. Why not? It should be 3,000 requests per second. You have to define some expectations that are reasonable. And one of the problems that we have in our teenagerness of web engineering is that our standards are not high enough. We're just looking to get lucky, right? Have high standards. Right? You should expect more. You should understand what's possible and expect some boundary within that. This allows you to plan. You have some reasonable expectations, you do your monitoring, you have your trending, you can look at where you should be tomorrow. And by coupling them back to business initiatives, when someone comes in and wants to do a marketing campaign and says, hey, we're going to probably pull in 85,000 new users, we're doing a 500,000 member rush, and we expect whatever conversion rate that is, 16% conversion rate. You actually have a plan. You have the last marketing campaign. You have all of the meters and the metrics, the IOPS on the disks for all of this stuff, and you can actually be an engineer. You can draw all this stuff together. And it allows you to ask questions. I don't know how many people turn monitor and they're like, yeah, everything's good, we serve traffic. They turn on the monitor and look at it and they're like, what is that? And they look at it and boom, 20% performance improvement across the whole architecture. Now, if you're already doing monitoring, you're already asking questions, you're probably not going to get 20% by, touching the first thing. But if you're not doing this and you don't have a cohesive plan for monitoring, the first time you turn it on, it will pay for itself the first day. It's not just about trending numbers. It's also about trending events. So the bottom graph is storage space, and when people fix problems with storage space. So this is a projection of a self-monitoring system. This is the storage space required to monitor the storage, all of the things we monitor. The top graph is a little bit more interesting. I don't even know what the numbers are. But I think there are events per second in the system. But the red lines are new account signers. So you can see the third red line from the left discovered a bug in the product that caused an actual complete outage. And you can track it down to that exact account. They launched their account, did some things in the system, and now it does 0 transactions a second. This also allows you to correlate the last 2 accounts. It's very unlikely that previous accounts suddenly decided to become active at that point in time. You can correlate all of these things. Imagine those red lines as code pushes, as SVN commits, as your chef repository updates. All of these different things should be tracked. All these events, it's up to you to decide whether they're causal or correlated, right? And this is the challenge. And when you look at graphs, your brain is like the best pattern recognition system in the world. You will start to ask questions. And hopefully if they're stupid questions, they're answered quickly. And hopefully if they're great questions, they're also answered quickly and you get great gains. So monitoring is really in there because you can't be scalable unless you're watching. You cannot improve on something you can't measure. If you say, hey, it's faster, I'm going to ask you how much, and you're not going to know. So you have to monitor things, otherwise you can't improve them. This is a recursive definition of that. So let's get into databases, which is more interesting. As Brian's normally crazy and interesting at the same time, the whole dirty systems. Stock market has done that for a long time, right? And stock trades come in, acting on data that's extremely old, like 350 milliseconds, for example, stock trading. You have a nuclear explosion that violates treaties. Remember the NANX crash from like 6 months ago? It was a one-day spike crash, and then they had to do all refund trades and stuff like that. The unauthorized reason for that is that one of the trading devices has a queue, all of them use queues, and they jam all the stock statistics in one, have an embedded system that processes them and answers questions at the end. The data that was coming in was timestamped, but it wasn't timestamped when it left the queue. And unfortunately, they implemented it as a soft real-time system instead of a hard real-time system. If that data gets old, it's actually much better for that system to die and crash than it was to cause the market to crash. Stuff came out of that thing hundreds of milliseconds too late. So there was one guy on the market doing high-frequency trading that was flash trading all of this stuff based on ancient information, 300 milliseconds old, 400 milliseconds old. So those systems exist. Adapting them to the web is an interesting concept because the dynamics are entirely different. But ACID and base and these complex event systems, the dirty systems, I think the architecture of the future, the architecture of the future will incorporate every single one of them. And if you look at Facebook or Google, people are like, oh, Google, you know, they're web scale, of course, right? Everything's map and reduce. No, it's not. There are large portions of their architecture that are map and reduce and batch. How many people here run a site with more than 100 million people on it? How many with more than 10 million people on it? And 1 million people. How many people run an RDBMS of some type or another, like MySQL or Postgres, Oracle, something like that? How many people run a noSQL system of some type or another? Whether it's almost all the same hands. You've come to this reality, which is good, that it's very unlikely that you will have an ACID system or a big system. You will have something that is both. You will have different parts of your architecture that are that way. So it's good to understand exactly what those things are. So it's a scale up versus scale out argument. And one of the books that I read recently, finally got around to reading it, is The Art of Scalability. And one of the things that they say in there is that scaling up is never a question. exposed to that concept. You have the liberty of planning. You have a system. It has many components. You know your potential audience. You know your business plan. You know how the system should operate. You can actually look at a component and say, if everything in the world went right, we got all the customers we wanted to, provided service to them all the time, and I doubled it, how many transactions would that be? How much storage would that be? How much latency is tolerable? You write the numbers down. It's very likely that for some of the components in the system, you don't need to scale out at all to solve those. And complex systems fail spectacularly. So if you can run 2 hot standby systems and scale up because you know that your trajectory will never exceed the capacity of what's available even today, you have eliminated a lot of failures that you will have. And you have allowed yourself the time to focus on real problems that are the scale-out problems, which end up being very hard because the systems that you build are complex and fail and interesting and hard to diagnose ways. So you plan your problem, you project it, you map it, and remember that new always equals dangerous with technologies. Always equals dangerous. So if you build it yourself, it's also new. It's dangerous. It does not mean you shouldn't use them. And there are plenty of people that how many people here run Cassandra? Right? A couple. Voldemort. A couple more. Somebody can call it a noSQL. A lot of people raise your hand to noSQL systems. MongoDB. Great. So, as I won't be as rough as Cancel on that one, but new is dangerous. Right? And you should be asking yourself questions like, when you adopt a new technology, what academic paper is this based off of? And if the answer is none, it doesn't mean it's broken. It's a variable in the equation. Right? You look at these things, you weigh them, you look at the academic paper that looks near it, you read it, and you say, wow, these were all problems identified. How do you address those? The answer, is not a good answer. All right? The answer is, we've identified that some of these aren't. You want an intelligent conversation about the answer. It means that the developers of said application have the right frame of mind to be developing an application that stores your data. And when I talk about data stores, I'm not talking about dirty applications. One of the things that Brian didn't mention, which I'm not sure he intended to mention or not, is that the idea that if data is on time, it's good, and if it's not on time, it's bad. Not only is it bad, it's trash. Most of the dirty systems that we deal with, the complex web processing systems, all data is trash after 1 second. It's whether or not it went into the engine or not. I'm getting a stream of data. I'm tossing hundreds of thousands of records per second into this real-time system. I don't actually store the memory. I just have to get the right answer out of the engine. Some of them I don't put in the engine because they're too old to be relevant. The ones that are relevant, I don't actually store. Some dirty systems, I'm sure, store them. Some don't. Some are hybridized. But for data stores, their job is to store your data. So make sure it works. So there's a common misconception that SQL means everything in one database. Right? SQL is a query language, a structured query language. RDBMS, right? That's a relational database, right? There are relationships. When you start to define relationships between data, that's when the single system concept comes into play, where I have data in the system, and I have this other piece of data that's related to it, so I need it in the same system, and as my relationships get complex, there's no way to track that. There are plenty of companies out there that run SQL and don't use relationships. Right? Anybody who's ever sharded their databases, and they put some users here and some users there, you can't have an acid-enforced relationship between the data on these different nodes. So, SQL is structured, ACID can't scale, the CAP theorem says so. The interesting part, Eric Brewer is a brilliant man. The CAP theorem doesn't directly apply to reality. The definition of C, A, and P are extremely hard to map to technologies like Postgres, MySQL, Mongo. How you define partition tolerance and availability and consistency in in that paper don't directly match to those things. So the theorem is a good one. Applying it takes some finesse in practice. You have a question, Mary?
I just wanted to say, just so that people don't misread, the slide doesn't say SQL can't scale. I've seen a lot of quasi-academic exposés of how SQL is not scalable on the web, and none of them have any academic rigor whatsoever.
Okay. So the point was that claims that SQL can't scale have no substantiated academic rigor behind them.
Right, but that's different from ACID can't scale.
That's different from ACID can't scale. So ACID can't scale is different. So people say that SQL can't scale. It's like saying that Ruby can't scale. It's like saying that Perl and Python or C can't scale. SQL is a language. So it doesn't make any sense. And you can have SQL as a language and adapt that loosely to non-ACID systems. Look at MySQL in its first release. It hardly complies with ACID, yet it provided SQL. Much better now. So many of the solutions don't scale, right? We need to break our problems into much smaller solutions. So one common thing with SQL is financial information, right? My shopping carts can be different in London and in Paris. That's fine. When I purchased an item, I was charged, and they said they shipped it. Like, I don't want it eventually consistent. I want it consistent now. Like, you charge my credit card money. Like, this is important. I want to pay for that. 1 million rows in a table, 100 million rows in a table, 10,000 transactions a second. That's easy for an SQL database, an ACID-compliant SQL database. You have 10,000 transactional sales a second. You can solve that problem. You're making enough money, right? This is not a financially encumbered problem. So things like inventory management and purchase logs and ledger systems for credit cards and things like that make a lot of sense to do in ACID. And there is no real sensible scalability constraint in that because you have a problem that you would love to have. You can't scale that. So noSQL. noSQL, nobody knows what it is, right? It was noSQL, now it's not only SQL. Who knows? If it's not SQL, it's also things like nails and hammers, right? Those aren't SQL. So I'm very confused about the whole thing. But they have some concepts that are common. The popular concepts are that there are no single points of failure. Not all of these have that implementation, but many of the noSQL systems actually have no single point of failure. Any node can die in the system. There's no special node, any node. Some of them are simply key value stores, other ones are document databases. Both have their place. A lot of them leverage consistent hashing. A lot of the Amazon Dynamo papers, which are the kind of the real world implementation of the consistent hashing papers that preceded it, where I have a set of nodes and I start to allocate my data amongst those nodes. I can add more nodes and it has good properties about that. Apache Cassandra uses that, Dynamo uses that, Voldemort uses that. And most of them sacrifice consistency for partition tolerance, which means that if I have 3 nodes here and I have 3 nodes there, and I divide them, they can't talk to each other, that the system is still available. I can still serve traffic, I can still ask questions, I can still put data in. People are like, that's awesome. You will get the wrong answer back. That's what consistency means, right? You're not going to get the same answer. And they're like, oh, that's not so cool, right? So when you sacrifice consistency, it's not always a bad decision, it's not always a good decision. You have to map it to your actual problem. Will it have unexpected outcomes for your business or your users or your transactional models? Not ACID transactions, but just like my experience as a user, do I get expected behavior back? Because that's what's really important on the web. The web application needs to act how I expect it. So consistency is dangerous there. What's even more dangerous, all of these things have habitual consistency, which is when those 2 partitions now talk to each other, they can reconcile their data, they can play forward, they can use things like collision, lost, grad school. So they can do conflict resolution, or they can do these things like factor clocks and network timestamps spin commits and all sorts of things. There's a lot of different ways to do this eventual consistency. If you misimplement, these technical details are hard. If you misimplement your promised eventual consistency, it's not even eventually consistent. It's like having an ACID database where you run commit, turn the power off, turn the power back on, and the data's not there. And that's the same thing. Right? When you have ACID and you say, hey, guess what? Durability. That means when I commit, assuming my disks function, which should have, because commit came back, that after a failure recovery, I should have the data. Eventually consistent noSQL systems means that eventually they will be consistent. I challenge everyone to pick a random noSQL implementation of eventual consistency, throw a bunch of data in it, partition the network, put it back together again, and see if your nodes agree. It's a hard problem, and it's hard to implement. So there's a long way to go. These are new technologies, and they're somewhat dangerous. Given that they solve problems, otherwise it's helpful. So noSQL does not mean problem solved, got down the silver bullet. I don't feel like I should have to counter that delusional argument, but I don't even know what problem to solve. Right? It's not a technology problem we're trying to solve. We're trying to solve a business problem. I have data for users. My users are on different coasts. I want them to be able to see each other's favorites and transactions, or each other's preferences for purchases and things like that. Those are business problems. This is just technology. So the idea that noSQL just solves the problem, we start to articulate the problem. Nobody solves it. And you've adopted a very different set of guarantees. That's the consistency argument. A lot of people, when they say, oh, I'll take availability, partition tolerance over consistency and availability. So ACID gives you CA, and noSQL gives you AP. And there's a lot of them that kind of bend it, give you a little bit of one, a little bit of the other, and kind of can allow you to make a trade-off. You're making a trade-off, and you really need to think about how that affects what you're storing. There are no silver bullets, less than enough. The data source is true. Yes. Most big sites run one RDBMS and at least one SQL implementation. A lot of them run two of each. So we have these different workloads in databases. We have wide write workloads. This is where you write a lot of different keys, for example, in a system. I need to change terabytes worth of data. So I think it's easier to actually start with narrow writes. Narrow writes, the definition of narrow write is I'm updating hot data, basically. I may have a terabyte of data, but I'm updating with the same record all the time. Narrowly writing to the data. Narrowly reading from data is things like a primary key lookup, where I'm returning one row of data. Right? I'm just getting a little sliver of data back. So I'm getting a narrow piece of data back. Wide reads, business intelligence systems. I have to scan 40 billion tools to get my answer back. Wide writes, I have to go update 40 billion tools. So these problems, as they get very large, there are different approaches to those. Wide writes, wide reads, highly federated data. I have thousands of nodes. This is what Hadoop does. You can do this in MySQL. You can do this using Postgres. What it means is that you have these technologies running all the nodes, and you have a data system above it that can fetch data from all of them. And this is what sharding is. Wide reads, same way. Narrow writes are interesting. Narrow writes are a problem because you have contention problems in data. There are 400 people trying to update the same piece of data at the same time. These are commonly things like counters. For example, how many users do you have on your site? Every time a user signs up, you have to add one to the same number. Okay? In a lot of systems where you're doing monitoring, you have 10,000 or 100,000 of these metrics that everybody's trying to update at the same time. The truth to that is why there's a lot of money in this from the financial market, because the financial market has the same problem, is that the best thing we have today still is one machine, fastest processor you can buy. Right? People are using GPUs to do this now. I mean, it's all about, if I put it on two machines, now I have to worry about them both agreeing. And they're light years apart compared to on the same piece of silicon. Right? So this is the problem, the narrow write problem. Usually it's just one box does the trick. Narrow read problem, where I'm reading the same data over and over and over again. I want as many copies as I can, and I want them to be consistent. So you'll notice that every single one of these things has SQL, highly federated SQL databases, and noSQL. And all of them. You can solve all of these problems with both technologies. Again, it's not really the tool that won't work, it's the competency of the implementer. You can do anything with anything. Square peg, round hole, no problem. So, just as a simple example, let's look at users searching profile data. I have profile data. I'm updating my first name, my last name, maybe even my status. Relatively low. Even if I have millions of users, 100 updates a second is pretty reasonable. It's trivial to handle this in any SQL database. 100 updates per second, even if it's 1,000, 5,000, 10,000. The problem is that I have users reading this data at enormous volumes. So I'm doing searches across users. I want to see everybody who has a status that looks like this or like that. So you're looking at basically 2 orders of magnitude higher in read volume than you are in the write volume. So other technologies are better for searching data than databases. That's the truth. I mean, so how many people here use SQL to actually do full text searching? Probably a couple. If it's low volume, it's not a problem at all. If it's high volume, you start to run into that. Should I really be getting 4 requests a second, or should I be doing 4,000 requests per second? So, I mean, this is a pretty simple pattern where you write all your records to a main database. Maybe you have a backup, that's fine. But then you queue all of that information, all of the updates out, and you update, say, a distributed Lucene repository, like Solar or something like that. So you're writing to a database because it makes sense. You want your data to be active. When people change their first name or their last name, or they change their state, you have a legal responsibility because the services you provide, they say they're in France, there's certain things you can and can't do with them. It has to be accurate. Searching could be a couple seconds out of date, actually, because different users are searching different things. So, master record, it lists on a queue for updated profile documents, and it collects updates for about a second. And it writes out the index and commits, and then goes and collects for a second, and then there are updates. Very simple. You can have multiple subscribers for this. You support multiple subscribers. So the different part about data storage, and I touched on this briefly, is some problems we can't afford to store data. And this gets back into the dirty applications. Event processing systems, intelligent event processing systems, and streaming databases. They're really popular right now. They've been around for quite some time. So it's one of those things where we really need to go look at financial services industries, stock trading industries. Those people care about a lot of data with questions being answered right now. So it's extremely important that we actually not reinvent the wheel here. We need to research, look at academic papers. Messaging. Awesome. So the reason messaging is such a fundamental underpinning of this is, how many people here use message queue somewhere in their architecture? Well, this is really good. One of the things that we first realized when we put a message queue in place is someone goes, I can listen to that data now? That's awesome. Right? I had this data going across the network. I didn't even know I could subscribe to that data stream. All these new services and features of architectures and efficiencies come out of being able to observe data in a multi-subscriber model. So now you start using message queues because usually the emphasis of that is, I can't afford to do that right now, so I will queue it and do it later. So the asynchronicity was the driving force for adoption, at least on the web. But the benefit we get from this is multiple observers. We get to do all sorts of awesome things in an architecture. And a lot of those tie back into monitoring. The CEP pattern. So we do a lot of things. We do a lot of this at MTI. I like RabbitMQ. It works really well. The CEP system we use is Esper. I don't remember the license on RabbitMQ, it's open source, but Esper is, I think it's MIT, or it's the Esper license, one of the two. It's pretty permissive.
What's CEP?
Complex event processing. CEP is complex event processing. Esper basically allows you to run an SQL-like statement on a stream of data, and the statement never ends. The query never finishes. It's always running and emitting the results as they match, which is really kind of brilliant. So what we do, with a couple of snippets of Java, as first GTL, it's in Java. They have a .NET version as well. So what we'll do is we'll create a little program that has Asper engine in it. We'll have a little API, servlet API, so we can add and remove queries in it. And we have it listed on AMP, on RabbitMQ. And then we can do, we run the queries and publish the output on the AMP as well. And what we can do is we can take all of our clients, like logs, for example, like Splunk, that sort of thing. Take all of those logs and just spit them onto the queue. And now they start to go into this complex event processing system, and you can run queries like this. Select start from HTTP logs where status code equals 500. That's correct, basically. Right? Select URI count star from HTTP logs in a 5-second window. Rolling 5-second window, group by URI. Snapshot every 5 seconds, limit to 20. That should be ordered by count star, not ordered by URI. This is a 5-second ticker of the most popular URLs in a rolling 5-second window across your site. This is a pain in the ass to run against the SQL database. Right? It's a lot of work because as you're inserting all of these records into the database, the indexes are getting bigger and bigger and bigger. It's hard to control the data flow. You're actually never really interested in old data. So this is really efficient. It's all in-memory built indexes built for running these queries. The other awesome things that you can do, a little bit more elbow grease, is that you can look at URIs coming to the system with their service times, say do a 5-minute rolling standard deviation of service times, and meet every URI that loaded more than 2 times the standard deviation outside the average of that window, which is basically saying, stream all the URIs by and their service times and show me that any that are out of scope, like anything on them. Too low, too fast, too slow. Show me anything that's anomalistic.
Does the window have a limit?
Limited by memory. The window has a limit. So this, I mean, you can do 1-day windows. This is the veneer on the top of the ETL language. You can do all sorts of crazy stuff like linear regressions. So you can do linear regressions of data. You can do derivatives. So you can say, take the derivative of this counter over the last 5 minutes and show me what's outside the standard deviation of something else. There are a lot of really interesting queries. And the beauty is that it's all from a message queue. So if you want to play with it, you spin this thing up, attach it to the message queue, and you've got a live feed. Do whatever queries you want. You can start asking really interesting questions about what's going on. And it's not limited to HTTP logs. This can be anything. Think about the SQL flow query log. Be nice. So, caching. I would be remiss if I didn't run through caching because it's the only reason the world works. So, this is what happens when you cache things successfully. You can actually survive I think that's a 20-fold increase in traffic without even, this was on 3 machines. So this is 3 machines running along. I think that peak there is at 250 megabits. So it's running along, each one's doing maybe 8 megabits, all added up. It's probably about 24 megabits. That's the curve at the bottom. And then go to 250. Right? On 3 machines. It wasn't running Ruby on it. Or Django, or anything else. It made use of caching. The reason the internet even remotely works is because of DNS and caching, brilliantly. The reason the internet hardly works is because of the lack of understanding of caching by web engineers. So let's fix that and understand how caching works. Caching has so many levels. It's a basic computer science concept. We have registers, we have L1, L2, cache, we have memory, it uses file system buffer cache, it uses database buffer cache, block caches. We have LRUs and ARCs in the system. Those are released recently used caches, adaptive replacement caches. Within apps themselves, the app is asking a question that's rather complicated, maybe not for the database. They need to remember that. We've generalized that in a lot of ways and put it as a service on the network. It's almost like a caching platform as a service, which is Memcached. Commonly abused, but brilliant technology that's very useful. And we have server-side caching on the HTTP level, which is reverse proxy. So I can put an HTTP server in front of my architecture that says, don't go back to the web server to get content that you know hasn't changed. Right? Then we have client-side caching, which we don't even control. It's in someone's organization, and it's in this conference. When you go out to the web, you're going through somebody's cache, and it's remembering stuff. That's why our website looks so fast. So all of this stuff is really important, and you can't screw any of it up or stuff doesn't work. Luckily, everything above the main memory level is someone else's problem if you're a web engineer, really. It's like a system software engineering problem. But you have to respect it and have to use it. So without intelligent caching, web would stop. Most websites stop. On dynamic pages, which is pretty much the entire useful web, right? We have different data sources. And we have every data source has different unique properties about it. It has calculation costs, right? Do I have to actually go calculate data, fetch it out of the database, right? We have consistency guarantees. Right? Does the data I'm looking at have to be the same, regardless of where I'm coming from in the world? We have accuracy guarantees. Does this data need to reflect reality right now? Or can it be 5 seconds late or 10 seconds late? Paying all of those things on every page load uniformly across your data is idiotic. Okay? So every piece of data needs its own defined caching policy. Whether or not you implement it separately is one thing, but you at least need to understand it. Each piece of data has its own accuracy, consistency, and calculation risks. So you would define that. And you don't have to pull all of this data before you deliver the content. This is the awesome part about the web, right? It's asynchronous now. You can send somebody the structure of your DOM on the far, crackpot end of the spectrum. I can send somebody the template of my page with no content in it whatsoever, load an asynchronous JavaScript, and populate all the HTML. Okay, that's probably not exactly what I want to do. I want to give them some sort of experience in the beginning. But you can do that a lot. So anytime a piece of data is expensive, you can decouple it from the system and pull it asynchronously. This has two awesome attributes to it. One, the page loads immediately, so people are happy when data comes in. But if you screw something up and you have a component of your architecture that's not working right, you still serve the page. It just never comes up. Right? The little piece of content, related information on the sidebar. Populate related information with an asynchronous search lookup. Right? If it breaks, at least the rest of the site works, because it's asynchronous. That's it. On time. So does anybody have any questions? It's kind of all over the place. No? So you cache your websites. So an anecdote really quick. We had a client that had their front page, and this is a communication problem. They would tell, the business people are like, when I make a change to the site, it needs to update immediately. So the site gets about 3,500 requests a second on the homepage. And so every request goes back to the web tier and hits, can't hit the database for that, so they hit an cache. So every page load runs a PHP page, pulls a template in, and it goes and fetches stuff out of the cache and constructs the page, 3,500 times a second. And they're like, it would be really easy, can't we serve this stale? They're like, no, it has to be accurate. Has to be accurate. And then you go in and say, we have 40 machines in our web cluster right now. We need to go to 80. I can make this entire site drop, because everybody's getting the homepage, right? It's almost 3,500 requests per second. I can drop this to 2 web servers, not have to grow the architecture, and support 10 times as many users if you let me have the homepage be 1 second old. And they said, that's not even old. Like, you said you had to be accurate. They're like, yeah, accurate. That's not stale. I'm an engineer. It's a million milliseconds old, microseconds old, right? It's a billion nanoseconds old. 1 second is old. So what do? You put a cache in front of it, and a reverse proxy cache in front of it that can serve 150,000 requests a second, and you say the TTL on that page is 1 second. Boom, done. That was it. And it was just a miscommunication between engineering and business on what old to do, right? So, but a lot of trees got it, so it's okay. All right, well, thank you very much.